beyond the sea, somewhere waiting for me. My lover stands.
My name is Bill Gady, for those of you who don't know me. And I came to Austria to find out what physics is about. I thought I knew. When I was in high school, I had this vague notion that physics was supposed to be rational. And one day I came across a question on the internet. A person says, is quantum mechanics irrational and illogical? And these are some of the answers he got. Why do humans want everything to be logical? People have this notion out there that, science is not supposed to be rational. These people are born, they go through this religious indoctrination. They go to church maybe. They hear fantastic explanations. And, then they don't expect a rational answer. So if you're wondering why we have Big Bang, black hole, and some of these fantastic theories out there, it's because a lot of these people have been conditioned since they were children to believe in these kinds of stories. You also have bombardment from Hollywood. We get zombies. We have travel to the past. And people stop understanding the difference between reality and fantasy. Here are some of the other answers. It is not irrational and illogical, just non-intuitive. Why should human logic and rationality apply to quantum mechanics? It's man's comprehension of such phenomenon that is illogical and irrational. These people miss the point. It's not that the universe works rationally and that we are not. It's that maybe, just maybe, our mathematicians, as I call them, they have not figured out how this universe works. If I give you a theory about angels, well, yes, I have a theory. Does this mean it works? Angel pushes the earth around the sun. It works. Does this mean that this is the way the universe works? No, and this is the issue. Okay? These are some of the statements from the people who founded quantum mechanics. It's not me telling you this now. You can say, I'm a liar, I'm a nobody, fine. Here you have Nobel Prizes. All three of these people are Nobel Prizes. This is what they have to say about their own theory. Niels Bohr, those who are not shocked when they come across quantum theory cannot possibly have understood it. Werner Heisenberg, can nature possibly be so absurd that as it seemed to us in these atomic experiments, they saw something, they said, we don't understand it. 50 years later, Richard Feynman says, no one understands quantum mechanics. Isn't that something? These are the people who founded quantum. They're the people who proselytize. They go out there and try to convince you, and they're saying they don't understand their own theory. And you say, how is this possible? Quantum has been around for, 100 years now? And you say, how is it possible that after 100 years, these people are telling you that they don't understand their own theory? What is it that they don't understand? We're not criticizing the equations. We're not saying that Schrodinger's equation is wrong. We're not saying that de Broglie's wave equation is wrong. We're saying that the explanations that they give us, the physical interpretations, are irrational. They're not wrong. They're irrational. And there's a difference. So all these people, they tell you that they don't understand their own theories. And you say, well, what is that they don't understand about their own theory? Well, let me give you, for instance here. What is irrational about quantum? Why it always will be irrational? There's no way they can rationalize this. You have two particles. This is the entire universe. There's no God, no devil, no you, no me, no heaven, no hell. This is all there is in the universe. Two particles. There is no way you can explain to me in a rational way how this particle gets this one to move. Not from a distance. We can all understand push, surface-to-surface contact. What we cannot understand is pull from a distance. Quantum will never be able to answer pull. And that's why quantum does not incorporate gravity, because gravity is some kind of pull force, whatever it is. So you cannot explain how this particle gets this one to move from a distance. Let's go a little deeper. This is the proton. This is the electron. According to the standard model of quantum mechanics, this is the hydrogen atom, right? Why doesn't the electron drift away? Why doesn't it fly away? What keeps it bound to the proton? What do the quantum people propose? Well, they say there's a field. Oh, we got a problem with the word field. Field is a concept, okay? It's a concept. What if I told you that my dog is tied to the doghouse by love? He's physically restrained by love. Or you can say he's tied by a leash, a chain maybe, but love? That's what we're doing when we're saying the field keeps these two particles together, right? But let's forget about that argument. We can see the field is a physical object. How does it do it? What's the physical mechanism of attraction? How does the field work? Is it like paste, like glue? Is it like tape? Is it like a vacuum cleaner? Sucking the electron in? Why doesn't the electron fly away? What's the mechanism? It's not sufficient to say, oh, it's a field. I could have said X. It's X. So what have you learned? You need to know what the mechanism of the field is. And now let's forget about that argument too. Ernst Rutherford, 1919, said an atom is mostly empty space. This is not the quantum atom. Quantum atom is this, empty space. That's the quantum atom. Mostly empty space. So there is no field. So we have three levels of irrationality. We're using a concept as a physical object. Then we're not explaining what the mechanism is, even assuming it were a physical object. And then, Rutherford says, forget about that anyways, an atom is mostly empty space. Now you see why we don't understand the theory. It makes no sense, okay? These are the problems with mathematical physics. We have a problem first with language, and I'm going to go over that in a minute. We have a problem with reification. Reification means you turn an abstract concept into a physical object and then begin to move the object around. You turn love into heart. Now you move the heart. And you say, hey, Ma, look, I'm moving love. No, you're moving a heart. You're not moving love. That's what we do here, reification. We have abstract concepts and that's what we play around with. Is this physics or is this philosophy? What is this? Because of that, we end up with irrational explanations. And because of that, we have lost track, not we, but the mathematical physicists, they lost track of the subject matter. We're not doing physics anymore. We haven't been doing for the last 100 years. This is not physics. So we're going to get to the subject of energy. All of you have a little pen and pencil there and a piece of paper. We're going to do a little test. How many of you have taken physics in high school? Almost everybody. Good. We're going to test you today. I'm going to mention a word. I want you to draw it. Okay? Very simple. I say a word, and you draw it. Straightforward? Any questions? Ready? First word. Triangle. Triangle. Please draw a triangle. Triangle. I can barely see them. Yeah, I guess. 3 lines, 3 angles. Very easy. Second word. Same word in German. Fish. Please draw a fish. Simple fish. No eyes, no mouth, all the scales. Little fish. Please show it. Okay, more or less fish. We all know what the word fish means. Third word, energy. This is what people draw. Some people draw a sun. Some people draw a lightning bolt. Some people begin to draw for me a power plant with the cables coming out. It's crazy. When in doubt, when you don't know what the word means, ask the Nobel Prize. He won a Nobel Prize, he should know. So let's ask Mr. Richard Feynman. It is important to realize that in physics today, we have no knowledge of what energy is. Here is a man who wins a Nobel Prize. All his explanations are based on the word energy. He's telling you we don't know what it is. This word has been around for 2,500 years, since the days of Aristotle, who's the first guy who wrote about it. We don't know what it is. Okay, so we don't know what energy is. Fine. All of you have taken physics, and you've heard of the word mass. We all know what mass is. It's the quantity of matter. That's what they tell you in high school. You take the test, and all you have to say is, you have A, B, C. You check B because quantity of matter. Well, let's see what they have to say. John Wheeler, Edwin Taylor, two famous gurus of gravitation especially, right? Nature does not offer us any concept of the amount of matter. Even if we could count number of atoms, that number would not equal mass. Notice that he's not telling you what mass is. He's telling you what mass is not. And he says what it is not is the quantity of matter. So, what they told you in physics in high school is wrong. It's not the quantity of matter. Okay, two words, time. We all know what time is, right? You go to school, you go to work. We all have to use time. St. Augustine, 5th century. What then is time? If no one asks me, I know what it is. If I wish to explain it to him who does not ask, I do not know. We have the same answer today. We have Stephen Hawking, famous British physicist, mathematician, and he tells us that he writes a book, a 200-page book, A Brief History of Time. The only word you will not find in the glossary is the word time. That's the subject, man. He doesn't know what it is. We have another fella. His name is Paul Davies. He's a Templeton Prize winner, $1 million, so it's not cheap. And he writes a book, 300-page book, about time. I guess it says it all, right? And the only thing he doesn't write about is about time. He doesn't know what time is. So we have all these words that these people use. They move around, they dilate, they move the mass from here to there, they turn this into energy, and none of them know what they're talking about. Of course, then they say, well, we don't understand our own theories. And then we get to the word force. I'm sure that everyone who's read a little bit about quantum knows that the word force is very important in quantum mechanics. Gauge boson, force carrier, bosonic particle that carries any of the fundamental interactions of nature. Carries a force, carries an interaction. Does a bird carry his fly? Does a fish carry his swim? Does a kangaroo carry his jump? You looked at Stephen Crosler's there. Remember the kangaroo? It makes no sense. This is irrational language. What do you mean you carry a force? How does a particle carry a force? They carry it in his back and then delivers it? Delivers pull? Delivers push? What is this? We had to invent this kind of language because it is all completely irrational. You have to convey a rational explanation. They don't do this. You'll never find a rational explanation. We get to the word point. Point underlies everything in mathematical physics. If you're going to do general relativity, they talk about an event. Event is defined as a point in space-time. You go to quantum mechanics, they talk about accelerating point particles. I think Alex is going to be talking about the Higgs. It's a point particle weighs, I don't know how many kilograms, but they accelerate this mass, and it's a point mass. So you ask the mathematician, what is a point? Very simple. A point, we all know what a point is. What is a point? So he takes the chalk, he hits it against the board, and he gives you something like this. And then he says, it's zero-dimensional. Zero, this has width, it's got height. What do you mean it's zero-dimensional? And he says, no, you're confused. You're looking at the dot. The dot is a pictorial representation of a point. Oh, my mistake. Sorry. So what's a point? Well, see, we pictorially represent location. A dot, a point is location. And you say, it's location, well, that's fine, but we have solids, cubes, spheres, pyramids. We have planes, squares, triangles, circles. And we have location. Location is not a geometric figure. How can we be putting it in the same set together with these physical figures. And that's the problem. They're using the object called the dot and the abstract concept called location, and they've merged them. They took the heart and they took love and they put them together and they built a point. And the point is more powerful than God. You can explain anything with that, because when you're talking about physics or the physical part, the explanation, you use the dot. And when you want to talk mathematics, you use the location or a number, whatever you want to put in there. So again, we have all these words. These are at the basis of mathematical physics. And they're all misdefined, they're all misused, they're all converted from concepts into objects. And of course, at the end they say, we didn't understand our own theory. Oh, great. Because of this, we end up with the wrong questions in physics. We've got the wrong subject matter. These people are not talking physics anymore. Here are some of the questions that the physics frequently ask questions to cite. They're saying these are the most fundamental questions of physics that they're investigating today. This is where your tax dollars go, right? They're saying, look, what happened before the Big Bang? I don't know. God was scratching his head. I don't know what happened before the Big Bang. Well, how is that relevant to physics? Big Bang is the moment of creation of time and space and everything. What happened before that? I don't know. What was there? Nothing? I don't know. Are there really 3 dimensions of space and 1 of time? Here they tell you they have proven space-time. You can't even publish a paper in any scientific magazine. You're censored for even raising the issue. They're saying space-time has been proven. You just need to read. You just need to educate yourself. This is the second question on their side. They say, are there really 3 dimensions of space and 1 of time? So their question is, here they censor you. They're the peer reviewers. They tell you what they've already proven, and now they're asking the question to themselves, is this really true? So they don't know. They're guessing just like anybody else. Why is there an arrow of time? I didn't even know there were Indians shooting arrows these days. We're in the atomic age. These people are talking about bows and arrows. Look at the issue. The issue is they ask a question of philosophy. Why? Why did you go visit your mother yesterday? Well, because I love her. Is that a question of physics? It's a question of philosophy. These people cannot distinguish a question of physics from a question of philosophy anymore. They're not even the subject matter anymore. Okay? Is there really a Higgs boson? Well, I'll let somebody else talk about that one. This is the big question they arrive at. It's trademarked, so please don't copy it. How can we merge quantum and general relativity? That's what they're investigating. Well, if both of them are irrational, we don't care how we're going to merge them because they have no bearing on physics. They simply are not in the subject matter anymore. So what is physics about? In the alternative. If this is not physics, what is physics? Physics is about explanations. I want to hear a rational explanation. And these people are so far out of the subject that they have a different idea of what physics or what science, they equate science with physics, what physics and science are about. They say, no, physics is not about explanations. Here we have a emeritus professor, Donald Simonek, and he says, science does not explain, science describes. So I describe a chair, 4 legs, 1 backrest, seat, that's science. I just described something. So we have a difference of opinion with him, very serious difference of opinion. But the important thing here is that at least he seems to understand that there's a difference between a description and an explanation. Most mathematicians out there are not even aware of that. They think it's the same thing. So what is the difference? Description, listing of properties or behaviors of an object. You have an object, you say this is white, it's got 4 sides. That's a description. I haven't understood anything, any explanation. I haven't explained anything with that. I just described it. An explanation is the prosecutor's version of how a phenomenon occurred. What happened? How did a magnet attract another one? Why doesn't the Earth fly out of the solar system? Please explain. That's what you need to explain. But describe and say the Earth moves around the sun at 30 kilometers per second, that's a description. What have you explained with that? That's just a question of establishing standards, the meter, the second, and saying, well, we measured and this is how fast it's going. It's a description. Even if you zero in on the perfect equation, what have you explained with that? Mathematics is not the language of physics. Mathematics is a descriptive language. It's made for describing. The language of physics is illustration. In physics, we deal with objects. And objects we should be able to illustrate, we should be able to move them around. Little Martians come to your house. Ooh, little flying saucer. They get you, they put you in their ship, take you back to Mars. They're not kidnapping you, they just want to show you their planet. They're so proud of it. And the Martian, who's your host, he says, "You want to see my new car? I bought it before we kidnapped you." "Yeah, sure, why not?" Go to a garage, and he shows you this. And you say, "Okay, that's new? Yeah, it's new. Okay, does it work? Does it run? Sure, you want to go for a ride? Oh, sure. I'll humor you. You get on, takes you around the block. How does it work? Does it work by magic? No, it works just like a car on Earth. What do you mean like a car on Earth? Yeah, it's got wheels and it turns and the rubber, the tires, hit the pavement, you move forward. What wheels? What tires? What are you talking about? There's no wheels or tires. This works by magic. Oh, I see what the problem is. See, the problem is that the wheels here on Mars, they give off an ultraviolet light. And you earthlings, you cannot see ultraviolet light. That's why it's invisible to you. But there are wheels there. And you say, now that you understand the mechanism, it's no longer magic. It's not mysticism anymore. It was mysticism only because you could not see the wheels. Then it was magic. But now he explains the process. He said, no, there are wheels there. It's no big deal. Now it's a piece of cake. You say, okay, I just can't see them, but they're there. And then you can explain how the car moves forward. So you say, okay, I got a thing to show you. Why don't you come back to Earth with me? You say, okay, let me show you something. He takes you back to Earth. You take him to your garage, and you show him this. And he says, how did you do that? That's magic. And you say, what are you going to tell him? Please make the invisible visible. Show me what is in between them. Now, I take two horseshoes from any horse, and they don't do the same magic. In fact, I can't imagine a horse running with magnets, stuck together all the time. How does it do it? There's magic. Well, hopefully you're not going to say, there's nothing there. Because again, two horseshoes do not attract each other. So if we have two regular horseshoes, they don't attract, and these two horseshoes, they do attract. So there's some kind of difference there. And hopefully it's some physical difference, or we're all crazy. We're doing magic. What does quantum say? Well, they do it with a field. Famous field again. Fine, we'll accept it as a physical object. What's the mechanism? Why, when I turn the magnets around, rotate one of them north against north, now they push each other apart? What's the physical mechanism? That's what we want to understand. There's not a single mathematician on planet Earth who can explain these two pieces of metal. That's the entire system. And they cannot explain this. We've got all these equations. We can tell you how fast it's going, how fast a particle travels through the field, but we cannot explain the physical mechanism of this little magic that Mother Nature does here for us. Okay? So what is the big question of physics? There's been only one question we ever needed to answer in physics for the last 2,000 years. It's the same question that Newton faced and his contemporaries faced 400 years ago. It's the question that everybody since then has avoided. It's the question that if we answer it, we know how the universe works. We're done with physics. We can all go home. That's how important this question is. If we answer this question, let me repeat this. If we can answer this question, we know how the universe works. At the micro level, at the macro level. We know it all. We can all go home. We're finished with physics. And that question is action at a distance. How does Mother Nature do her magic from a distance? Hopefully we put something in there more than a concept. We can't say energy. We can't say mass. We have to put a physical object there. You have to put a dog. You got to put a chain, something in there. You can't keep doing it with concepts. This is the only question we need to answer in physics. So, here's another piece of magic. You can say, well, I don't know how the submicron world works. I can't see in there. I can't pry open the atom. Magnets, macro world. Now, how about this? This is the macro world. Here we have the moon going around the earth. How does it do it? There's two pieces of stone. There's two stones, two rocks there. And we cannot explain why the moon doesn't fly away. Magic? There's nothing there. Are we going to put a field? Okay, put a field. How does it do it? Please explain the magic trick. You go to the show. You see the magician cutting the woman in half. Curtains closed, curtains open, and a woman comes out there. Ta-da! Magic. But it's a trick. So please explain the trick. That's what we need to do here. Explain the trick. It's easy to say, well, yeah, he cut her in half in 2 minutes. The saw went at 5 kilometers per hour. Yeah, that's great. How did he do the trick? Description anybody can describe. You cannot do physics without objects. The language of physics is not mathematics. The language of physics is illustration. You need to make the invisible visible. We need to explain action at a distance. Here's the photoelectric effect. That's Mr. Einstein there. He won the Nobel Prize in 1921 for his alleged explanation of this phenomenon. What did he explain? He explained that light consists of particles, of discrete particles. And he said, actually it was Max Planck, but I guess he took the credit, Einstein did. You have light striking a polished metal plate, and a current runs. Just light hitting the metal plate. So the first thing, you cannot say that light is nothing. You cannot say, like some wave theorists say, it's the undulation of nothing. There's nothing there, but it's undulating, whatever it is. It's vibrating, it's moving. No, we have to have something there. And Einstein said that something are particles. Okay, that's fine. You say it's particles. Let's go with particles. We got a problem with particles because here we have the checklist of light. Any proposal has to pass this checklist, and you're welcome to modify the checklist. You are welcome to take things out and justify why you're taking them out. You can put things in if you want to justify it, fine. But here's the basis for anyone who wants to make a proposal for light. It's got to pass these things. It's got to be an object, some kind of body. And he's saying that it's a particle. Okay, that passes the first one. Does it start at the atom? Yeah, you can postulate that the particle starts at the atom, flies away. No problem. But where do we run into trouble? We run into trouble with the wave properties of light. Light has wave properties, and you cannot explain them with particles. For example, you cannot explain the oscillation around an axis. You cannot explain Faraday and Maxwell laws. The electric field generates the magnetic field generates the electric field. You cannot explain why the electric field, here you have the wave, right? And it oscillates along an axis. The axis is straight. You point a laser pointer, that light is straight. So you have a vibration along some kind of imaginary axis. Why does it do that? What's the magic? Right? You can't do that with particles. Frequency, wavelength, amplitude, none of those properties apply to particles. In fact, there's only one issue that you need to look, and that's this. Here's a particle. It's oscillating around an axis. So here you could say, well, the wave is made of particles. Fine. What moves the particle down? What moves the particle up? That's all you got to answer. You're going to use magic again? You cannot have a wave made of particles. So the particle hypothesis does not answer many of the properties of light. And this is the problem that they have. It travels fast. Yeah, you can just postulate. It says the particle travels at 300,000 kilometers per second. Okay, so it passes that test. What it doesn't pass is the next test. C equals frequency times wavelength. C is the velocity of light, 300,000 kilometers per second. And we know it's a constant, or at least that's what it seems to be. If you raise the frequency, you must lower the wavelength. If you raise the wavelength, you must lower the frequency. They are inversely proportional. How do you explain this with particles? You can't. There's no reason for. Well, why can't both of them go up? Why can't you increase the frequency and the wavelength and travel faster than light? Is there any reason to stop you? I mean, you can postulate, you can bring your magic wand and say, it is so and that's it. Fine, but you have no justification for that. Does it travel rectilinearly? Well, here's the sun turning around. It throws all these photons. It looks like a water sprinkler. We would never have light travel in a straight line if it's made out of discrete particles. If one particle is not tied to the other one in some fashion, some physical way, they would just, twirl around. You would be scanning, in curves, constantly in curves. So the particle is a lousy hypothesis to explain light. You simply can't. It's not a good candidate. What do we propose instead? Well, we're saying, what if light were a rope instead of the wave that we've always seen all these years? The rope binds two atoms. Every atom in the universe is bound to every other atom in the universe through some kind of electromagnetic rope. Well, let's see how this one does. The wave is a concept. Rope is an object. You go to the hardware store and you say, give me a rope. And they'll give you something that looks like this. You can bring and touch it and bring it to me. Ask them for a wave. Bring it here and tell me what they sold you. Or ask them for a field. Don't bring a football field. Bring a little magnetic field. That's fine. But you can't bring a field. What are you going to show me? There's nothing. It's a concept. Wave travels one way. It starts here and it goes to nowhere. And what we're saying is the rope binds any two atoms. One atom sends the torsion to another atom through the rope and vice versa. The signal goes both ways. I got my it's called the Bill Gates rope machine. The only purpose of this device is to show you how the light can travel, right? And it's a homemade device, real quick, for showing this. The signal goes both ways. Okay? Both are. Did anything move? Did anything go from here to the other side of the room? Did waves come across? No. It just twirls in place. Every time we measure, for example, frequency, what we're measuring is a cross-section of the rope, right? It's a different concept altogether. You see the bouncing for a cross-section of the rope. That's what we've been measuring. When light passes, say, a glass plate, that's what we're doing. We're cutting the rope. That's where the rope ends in an atom there. And whatever we measure, we're measuring the blips for a cross-section of the rope. Wave is dynamic. You take your little boy to school. He says, Daddy, a wave. No, son, that's a flag. You take him to the beach. Daddy, a wave. No, son, that's water. That's the ocean wave. Wave is what it does. You take a laser pointer. Right? He says, Daddy, a wave? What is it that's vibrating? What is it that is waving? There's something there, right? And so the wave is dynamic already. You can't say the wave is waving. There is no physical object called a wave. Wave is the word we use to describe whatever's already moving there. You got to tell me that whatever is. That's what physics is about. Well, rope is static. Here's a rope. You see it before I move it. Before I go into motion, first I show you what I'm going to move. Now I move it. So you can understand. You don't need to be a physicist for this. A 10-year-old kid can see this. You got a wave, you move it, okay. Torsion is what's really flowing. The torsion on the rope. It's a 3-dimensional wave. It's a totally different concept. How does the rope pass the checklist? Well, it is an object. It starts at the atom. It ends in the atom. Both ways. It's symmetric. It oscillates around an imaginary axis. I put an axis there just so you can see. Yes, if the rope is pulled tight, there is an axis. In fact, the way I built this, I put a clothes hanger I stole from my grandmother, straighten it out, and there it is. There's your axis, right? Faraday, Maxwell laws, the electric field green induces the blue magnetic field. The blue magnetic field induces the electric field. It's there. We have, does the electric field go perpendicular to the magnetic field? Yes, the threads. We have frequency, wavelength, amplitude. All the features are there. You could not distinguish the difference between a wave and a rope as a model. But here's the clincher. It does travel 300,000 kilometers per second. Well, I brought a test here. If I can get 2 volunteers. Can I get 2 volunteers here? 2 people? Anyone? Come on, Jan. Watch that camera. We're going to do a test so that you can see whether one stands over there and the other one here, right? And what I want you to do, just hold the rope. Just hold it. And I want you to send them some, transverse waves. Now you can almost see how fast it travels. Move it fast. Okay? We can almost see, we could film this. We could say, well, yeah, it travels, but it travels quite slowly, right? Now pull on the rope. Both of you pull on the rope. We're going to do something different, right? If we had a camera, we could film this. Pull tight, right? And that thing moves instantaneously. The vibrations move directly in there, right? That's fast. Here you have 300,000 kilometers per second, almost. And we're not tight yet. I mean, if this is really tight, that's almost instantaneous. Now we know why it's so fast. Now we have a reason for fast. Otherwise, you have to postulate. You say, oh, the particles just travel fast. Oh, okay, great, you know. Okay, you get paid later, not now. Where is it? We have also C is equal to frequency times wavelength. Well, you can see that if you have a rope, right, and you torque it more, for the same amount of rope, I get more links, and each link is smaller. The wavelength is shorter at the expense of frequency. And now I unwind it. Now the links are longer, right? But what do I have? Well, I have fewer links. Now we can, this is the equation of a rope. That is the equation of rope. There's no other thing you can use to simulate that equation. And here, well, I see it show it in a little more detail. Okay? The longer you make the links, the fewer links you can fit within a given length of rope, and vice versa. C equals frequency times wavelength. But above all, I can't explain, it's beyond the scope of this presentation to go into gravity, but now we can see why the moon doesn't fly away. If every atom on the moon is connected to every atom on the earth through electromagnetic ropes, then we have a physical restrainer. Now we see why the moon doesn't fly away. And here we have the system, sun, earth, moon. Again, we can see why none of them flies away. They're all bound together by electromagnetic ropes. There's a physical restraint. I don't say field anymore. I don't say mass, time. I say, look, there's a rope. There's a bunch of ropes. Now we understand. Now whether you believe the theory, that's a different story. But I can give you a physical interpretation, something that you can put your teeth to, whether you accept it or not, right? Questions people usually ask me is, why can't we see the rope? You know, what test should we run to find out it's there? Well, there is no test. Let me show you why. Can everybody see this little line there? This is the edge of an atom. That's the edge of another atom. You're talking about something so small, so thin. There's no way you're going to see. We can't see atoms. And you're trying to say, well, I can't see the rope. Sure, you won't see it. The other issue is that you use the rope to see. The rope comes perpendicular to your eye. It stimulates your eye, you know. And you're trying to see not the atom, which we can't see, but you're trying to see the rope that unites two atoms. You'll never make it. You can only postulate. You can say, how would we understand it? Well, if I assume that light is mediated by a rope, then yes, I can understand it. Again, whether you believe it or not, that's a separate issue. We can see atoms. And here, I did a little test at home, little pan, and you will see the laser light come into being as soon as the vapor goes through there. Now you can see light. Why can you see light? Is it because now you have special eyeballs, Superman eyeballs, you can see in there? No. The reason you can see it is because the light is hitting every water molecule from the vapor and reflecting it to you. If you do this in space, you will not see it. In fact, you can't see it here. Before the vapor really is thick, the fog is thick, you will not see, you don't see it there barely. You see more of it as soon as there's more vapor coming from the pan. Then the laser comes into being. You can't see light. You can't see light itself. All you can do is postulate it. Okay, so to finish up, the language of physics is illustration. Okay, we don't use concepts, we use physical objects. The theory of physics is a movie. You should be able to make a movie of your own theory. Like I did here. I should be able to show you, and you should be able to see me. I should be able to keep my mouth shut, and you should be able to see my theory with your own eyes. Whether you believe it or not, that's a separate issue. But at least you will understand it. Physics is about explaining and understanding. Physics requires an object. You have to make the invisible visible. That's what action at a distance is all about. Please tell me what's happening in that magic world that I cannot see. Make the invisible visible. Show me the tires of your car. And I'm saying that the invisible agents that mediate phenomena are the electromagnetic ropes. If we make that assumption, then we can at least make some sense of this universe. And it's not hopeless. Thank you.